Okay, so for this section, we are going to talk about chapter 6.4. And chapter 6.4 deals with one of the more important formulas that we are going to talk about in Math 150, and this deals with the central limit theorem. So what I want you to do when we're done talking about this is just come away with some understanding of the basic tenets of the central limit theorem. Because what the central limit theorem allows us to do is it allows us to make inferences based on um, knowing information about a sample mean. So a lot of times, as we've discussed about numerous times in this class, it's very difficult to get your hands on a population mean, right? It's very difficult for us to figure out information about mu. Just getting a hold of a population in general is a difficult thing to do. So what we're going to do now is we're going to talk about how we can use sample means to make inferences about population means. And the central limit theorem allows us to do that. So again, don't worry if you're not 100% on board with what the central limit theorem tells us, but what I do want you to know is I want you to understand a couple basic tenets by the time we're finished talking about it today. So let's start off with this beginning introduction. The central limit theorem states that the sampling distribution of the mean approaches a normal distribution as the sample size increases. This fact holds especially true for sample sizes over 30. Now, there's some interesting things that we need to unpack here and some interesting things to talk about. So let's talk about this first bit, which says the sampling distribution of the mean. So what does that mean when we talk about the sampling distribution of the mean? So here's what we're looking at when we talk about the sampling distribution of the mean. What we're going to do is we're going to see that we're starting off with some kind of population. We don't know what the population looks like. It can have pretty much whatever general shape we want. Now, this population has a mean, and we're going to put the mean right here. We're going to call that mu. When we talk about the sampling distribution of the mean, what we're going to do is we're going to draw a bunch of samples from that mean. And so we're not going to say how many, we're just going to draw a bunch. Let's say that we draw a bunch of samples of sample size 10. So we're going to choose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we choose these 10 data points. And then we're going to find the mean of those 10 data points. So I'm going to call that x bar 1. And then we're going to choose another 10 data points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're going to find the mean of those 10 data points. I'm going to call that x bar 2. And we're going to keep doing that. And we're going to do that over and over and over again. And again, we don't know how many, because we're unsure of what the population size is. So we don't know how many samples there are altogether, but we're just going to keep pulling out samples of sample size 10. And then we're going to graph them. So when we say the central limit theorem states the sampling distribution of the mean approaches a normal distribution, what's neat is that it doesn't matter what that original distribution looked like, what that parent population looked like in the beginning. When we go to graph these guys, these sample means of sample size 10 that we took, the graph of them has a very normal shape. And that's what that tells us. The central limit theorem states the sampling distribution of the mean approaches a normal distribution as the sample size increases. So if we take, let's say, 15 of these samples of sample size 10 from here and graph them, well, we're not going to have something that looks exactly normal. It could still have maybe this pointed little mountain appearance to it, or maybe something that's a little bimodal. But as our sample size increases, and if you take a look over here, it says this fact holds especially true for sample sizes over 30. Once we hit that threshold of that sample size being over 30, then we're going to get a graph that looks fairly normal. Now, if we have a graph that was ridiculously not normal in the first place, say something that looked kooky like this, then we have to take more than 30. We have to take more sample sizes over 30 in order for us to get a shape that's a little bit more normal. But the central limit theorem allows us to generalize about the sampling distribution of the mean. Okay, so let's make sure you understand exactly what we're talking about when we say the sampling distribution of the mean. Let's take a look at this example. And I didn't put this example in your notes, but I still want you to understand it. And so here's how sample mean behaves. let's say that birth weights are recorded for all babies in a certain town. Okay, so let's say that we recorded all of the birth weights of the babies that live in NYC. And we know their mean. So we know what mu is. We know the mean weight of their birth is 3,500 grams. Okay, so that's mu. And the second bit says, if we collect many random samples of 9 babies at a time, how do you think the sample means will behave? Okay, so we have a mean birth weight of 3,500 grams. And from here, we're collecting a random sample of 9 babies at a time. So let's say that there were 20,000 babies born in New York City last year. We're going to choose 9 of those 20,000, and we're going to call that our X bar. And then we're going to choose 9 more of those 20,000. We're going to call that X bar 2. And then we're going to choose 9 more of that 20,000. We're going to call that X bar 3. And if we continue doing that, like I said before, we're going to have this graph that has this very normal appearance, this low, high, low appearance. So some sample means will be low. So some of these X bar 1, X bar 2, X bar 3 will be low. So some of these guys will be down here. Let's say 3,000 grams. Some of them will be high. Let's see over here, we'll call these guys 4,000 grams. But what you will see in repeated sampling is we would expect that the random samples will average out to the underlying population mean. So what that means is the sampling mean is equivalent to the population mean. The sampling mean, or the mean of all the samples, is equivalent to the population mean. Now that talks about the center of it. So one formula that I want you to be comfortable with is this formula, and we're going to talk more about it later, but you'll see that, and there's a little bit extra stuff. I wrote it down here. This is formula number 1. The mean of the sample means is equal to the mean of the population. So the mean of the sample means coming from some population distribution is equal to the mean of the actual distribution. So we can talk about the center of the sampling mean. Now for the spread, and right, when we talk about spread, we're talking about here standard deviation. For large samples, we might expect that sample means will not stray too far from the population mean of 3,500. Okay, so a lot of our means will be hover around somewhere here around 3,500. Sample means lower than 3,000 or higher than 4,000 might be surprising. So it would be strange for us to collect 9 babies at a time and have a sample mean that's lower than 3,000 grams, and to collect 9 babies at a time and have their mean be more than 4,000 grams. For smaller samples, we would be less surprised by sample means. So that is, if we collect 2 babies at a time rather than 9 babies at a time, we would be less surprised that they vary a lot more. In other words, we expect greater variability in sample means from smaller samples. So sample size will again play a role in the spread of distribution of sample measures. So what this means now we're talking about the spread is we're talking about the standard deviation. And so the second formula that we're going to look at here, and I'm going to head on down here, we're going to talk about what that means, is the standard deviation of the sample means is equal to the standard deviation divided by the square root of our sample size. I'm going to write that over here. So the standard deviation of our sample means, is equal to the standard deviation divided by the square root of our sample size. And what this tells us is as we gather more information about our population size, as our n value increases, our standard deviation is going to decrease. So we're going to have less error, and our standard deviation is going to get smaller as we collect more samples. So the standard deviation of our sample means is equal to the standard deviation divided by the square root of our sample size. And lastly, if we want to talk about the shape, sample means closest to 3,500 will be most common. So like we said over here, we're going to have most sample means coming within the original population mean, which was 3,500, with sample means far from 3,500 in either direction, progressively less likely. In other words, the shape of the distribution of sample means should bulge in the middle and taper at the ends with a shape that is somewhat normal. So we're going to have a shape that looks like this. And so the important part that we're going to take away from here is as the sample size increases, the sample mean and standard deviation will be closer in value to the population mean and standard deviation as the sample size increases. So that means the more samples that we can get, right, the closer we can actually get to our population samples, to our population size, the less likely that we have, the less error that we're likely to have in our computation. So let's take a look at this. This central limit theorem tells us no matter what the distribution of the population is, the shape of the sampling distribution will approach normality as the sample size n increases. So the reason this is useful, or how we're going to use this, is, as I said before, we do know that it's difficult for us to get information about a population. So what we're going to do is we're going to use the sampling distribution. We're going to get a bunch of means from samples to help us make informed decisions about the population mean. And it allows us to make very good estimates of the population mean based on this. So again, as we said before, as the sample size increases, the sampling error or the standard deviation will decrease, because we know that the standard deviation of sample means is equal to the standard deviation divided by the square root of our sample size. So here's something to illustrate this up here. The central limit theorem tells us no matter what the distribution of the population is, the shape of the sampling distribution will approach normality as the sample size increases. So let's take a look at a few different examples of some shapes that we started with in the parent population. So you guys know this as normal. Right, here's a normal curve. Here's a uniform distribution. Here's an exponential distribution. And here's a parabolic distribution. So if you take a look, this is our parent population in this first row over here. And in the second row, this is the sampling distribution of x for n equals 2. So what that means is they took a sample of size 2 and then plotted the mean. Took another sample of size 2 and then plotted the mean. Took another sample of size 2 and then plotted the mean. So if you look, anything that starts out normal was going to continue to look more and more normal. The mean stays the same. I'm going to put the mean over here in red. If you can look, the mean, remember the mean represents the high part, that's staying the same. But if you notice, the spread or the standard deviation is getting smaller. Here's with sample size 2. Here's with sample size 5, the standard deviation is getting smaller. Here's with sample size 30. And it turns out that 30 is this kind of sufficient number, as we talked about before. Once you have a sample size of 30, then we're good to go. Then you have something that's fairly normal. Again, unless the original distribution is insanely wonky, then we have to do more than 30. But 30 is fairly acceptable with most statistics. So, okay, here we're starting off with a rectangle. What happens if we take sampling distributions of x for n equals 2? So I pull off 2 values from here and I take their mean and I plot it. I pull off another 2 values, I take the mean and plot it. Well, we get something that's triangular in shape. It doesn't look normal. But notice the mean doesn't change for all of these. It's still the population mean. And now take a look at the shape when we have sample size 5. So here I take 1, 2, 3, 4, 5 values, plot the mean. 1, 2, 3, 4, 5 values, plot the mean. Notice that the standard deviation is getting smaller. Notice that the mean stays the same, but notice once we get it n equals 30, we have something that is a lovely normal bell-shaped curve. Same thing for exponential curves. It starts off as exponential. We take a sample size of 2 and we plot those means. We get something that looks like this hill. We get the standard deviation here. Same thing, if you look, the standard deviation, the spread over here almost looks like this. Standard deviation is getting smaller and the mean is staying the same at all of these values. Same thing with the parabolic function. The mean stays the same, standard deviation gets smaller. As our sample size increases, as we take more means and the sample size increases for those means, we get something that's more of a normal distribution. So this is basically what the central limit theorem tells us. As the sample size increases, the distribution of sample means will approach the actual population mean. That's this. The mean of x bar is equal to the mean of the distribution. So it's really helpful when we don't know what the mean of the population is. We can take a mean of a ton of samples and that will give us a very good approximation as to what the mean of the actual population is. Now, the central limit holds true for any distribution. assuming our sample size is at least 30. Remember that 30 is that magic number that we talked about up here, that's going to give us a shape that's relatively normal. So we have a few restrictions here. We can use the central limit if we have a sample size that's at least 30, or if we don't have a sample size of 30, but the original parent population comes from a normal distribution, right? If you look at this guy that started off as a normal distribution, the shape, the spread doesn't change too much, and we know that the mean stays the same, but we still have that normal shape. So if either one of these two things happen, if the sample size is at least 30, or if we don't have a sample size 30, but we know that the parent population comes from a normal distribution, we can use the central limit theorem. Well, what happens if our n is less than 30? So if we have a sample size that's less than 30, or if we don't know anything, or if we know nothing about the parent population, if we know nothing about the parent population, I'll call that we know nothing about PP, then we cannot use the central limit theorem. So we can't use the central limit theorem. And the central limit theorem, I'm going to abbreviate that as calling it the CLT. We can't use the central limit theorem under those conditions. We'd have to use some bootstrapping methods to help us determine some information about the population mean. And C again says, given a sufficiently large sample, the mean of all samples from the population will approximately equal the mean of the population, which is pretty much the same thing as saying A. It looks like I said that twice. So now if you're kind of a little bit understanding, but not 100% of the way there, it's okay. I want you to understand these three formulas, what they mean, and how to apply them for these next few examples. So like I said before, we already know that the mean of the sample means is equal to the mean of the population. So that's one formula that I want you to think about that. We're going to come up with that in a little bit. You don't have to memorize this, but you do need to know that this is going to come into play. Now this you do need to know. And what we're going to do in formula number 2 is we're going to talk about how that applies us to formula number 3. So if we don't know the standard deviation of the population, again, it's really hard to get our hands on that. If instead we know the standard deviation of our samples, right? That's what that means. This is the population standard deviation of our samples. Then that's the same thing as saying the standard deviation divided by the square root of our sample size. Now, this part over here becomes important because we're going to start talking about how to find probabilities now. Not just of single values, but we're going to talk about how to find probabilities of sample means. So we're going to talk about how to find the probability of X bar or a sample mean. And when that comes into play, we're going to use, now you guys remember we talked about the formula before that Z is equal to X minus mu over sigma. Well, instead of finding, and this X was a single value, an individual value, instead of now finding the probability of an individual value, now we're going to find the probability of a sample mean. So we're going to replace X with X bar, subtract from that the mean, that's no different. Now in the denominator, do you see how we had the standard deviation here? Remember, because we're dealing with sample means, now our standard deviation is going to be rewritten as the standard deviation divided by the square root of n. So the idea is we use one formula in one circumstance and another formula in another circumstance. We're going to use, I'm going to call this Z1. We're going to use Z1 when we want to find Z values or probabilities. Let me write this out. Find Z values or probabilities of single values. Single values or individual values. We're going to use the second formula if we want to find, if we want to find Z values or probabilities of sample means. So the formulas look almost exactly the same. That's true because they are almost exactly the same. And that's the really neat thing about the central limit theorem is it allows us to make inferences based on a good sample mean. But the one way that they do differ, again, is remember that we're replacing this individual sample with a sample mean. and that the standard deviation, because we're dealing with the mean, and that's what formula number 2 tells us, the standard deviation now is the same thing as saying the standard deviation divided by our sample size, divided by the square root of n. So I think it's time for us to look at a couple examples. And again, these are the formulas I really want to make sure that you refer back to. Z1, we'll call them Z1 or Z2. And Z1 is the formula we use if we're looking for a probability, if we're looking for an indicated Z value of an individual value. And Z2 is the formula we're going to look at for finding the probability or the Z value of a sample mean. Okay, so let's take a look at 2 examples. And for this, I'm going to ask that you make sure that you have your calculator with you. So please make sure that you have your calculator next to you, and make sure that you have your Z chart as well. And I posted the Z chart in Blackboard for you. You can continue, you can print that out and continue to refer back to it. Let's take a look at this first example here. So assume that the average 9-year-old girl weighs 65 pounds with sigma is equal to 4.3. If weight is normally distributed, let's find the indicated probabilities. So part A says, a randomly selected girl weighs more than 66 pounds. Now this is what we just talked about in chapter 6.2. We're going to talk about how we convert, and remember we started with x's, then we're going to convert x's into z's, and then we're going to convert z's into p's, right? Because it's asking us to find the indicated probabilities. So let's find the indicated probability that a randomly selected girl weighs more than 66 pounds. Now the part we really need to focus on here is that this is an individual. This is a randomly selected girl. So that means we're dealing with that first formula. We're dealing with that Z1 over there. And I'm just gonna, sorry, hold on one second. I'm just gonna insert a little bit more space here because my pen is pretty thick. Okay. So let's figure that out. So find the probability a randomly selected girl weighs more than 66 pounds. So we want to find the probability that x is greater than 66. Now we're starting with x. We're going to convert x's into z's. So remember the formula we're going to use is this first formula, the z1, because it's an individual value. So to convert to z's, we're going to use z is equal to x, which is 66, minus mu, we know is 65 because it says here the average 9-year-old girl weighs 65 pounds, divided by sigma, right? And sigma over here, we know that sigma is equal to 4.3. So 66 minus 65 divided by 4.3. And we get 0.23. Now remember, z values, we're always going to round them 0.23. We're always going to round these guys to 2 decimal places. Okay, so we want to find the probability that z is greater than 0.23. Okay, so I'm going to screen share now my entire computer because I have a copy of the z chart over here. Just give me 1 second. Let me share my entire computer. Here we go. Let me make sure that we share. It's on the desktop. Sorry, I'm making sure that that's okay. Okay, so we have the entire desktop that we're sharing here. So when we talk about finding the probability that z is greater to 0.23, I am going to go to my z chart, which is over here, and I'm going to go to 0.2, which is right here, and 0.23, remember that 300ths, and excuse me, 0.23 is intersecting right here at 0.5910. Now also remember that z charts give us area to the left. Right? And when we say find the probability that z is greater than 0.23, this is actually area to the right. So we're looking for the area to the left to find the probability that, excuse me, we're looking for this area to the right to find the probability that z is greater than 0.23. And again, on the z chart, it's giving us area to the left. So remember, we subtract that value from 1. And 1 minus 0.5910, we get 0.409. Okay, so the probability of finding, and I'm sorry, this should probably say a randomly selected 9-year-old girl. weighs more than 66 pounds. And there's a 40% chance of that happening, right? And it makes sense right here that this is about 40% because, again, this is over here to the left of it is 59.10%. Okay, so let's go on to the next bit of this, which says now, and I'm going to go back home and I'm going to put some more space in between here. Sorry, not over there. I want to put space over here, which says find the probability that the average weight of 16 randomly selected 9-year-old girls will be more than 66 pounds. Now, I hope you can see that we're no longer dealing with an individual value. Now, when we're looking for the probability of 16 randomly selected 9-year-old girls, we're dealing with a sample mean. So that is, if I were to collect a sample, if I were to collect the weights of 16 9-year-old girls and then find the average of their weights. So I'm dealing with the sample mean. That means when I go to convert to z's, I'm going to use this second formula over here. So the first bit's the same. Let's find the probability the average weight of 16 randomly selected 9-year-old girls would be more than 66 pounds. We're going to start off with that being the same. We want to find the probability that x is greater than, that x bar is greater than 66, right? Because here we're dealing with the sample mean. Now, knowing that we're dealing with the sample mean, we're going to use that second formula, which tells us that z is equal to x bar minus mu over sigma divided by the square root of n. So let's fill these values in. First of all, our sample mean is 66 pounds. And our mean, our population mean, we know is still 65 pounds. The standard deviation we know is 4.3 pounds. M, the number that we have in our sample size here is 16. Okay, so when we go to figure this out on my calculator, I'm going to do the numerator first. 66 minus 65 is 1. And then in my denominator, 4.3 divided by the square root of 16. And this is the same square root when we were figuring out standard deviation before. So 4.3 divided by the square root of 16 is 1.075. And 1 divided by 1.075 gives us a z value of 0.93. Okay, so we have a z value here of 0.93. So finding the probability that x bar is greater than 66 is the same thing as saying find the probability that z is greater than 0.93. Now again, converting this z, remember we go from x's to z's to p's, now we're going to convert that into probabilities. I'm going to look up 0.93 in my z values. So here's 0.9, here's 0.93, and it's 0.8238. Again, remember that this is giving me, that I'm looking for here, that we're asking for area to the right. And when we read the z-chart, that gives us area to the left. So we're going to subtract that off, 1 minus 0.8238. And we get an answer of 0.1762. So we have a 17.62% chance of having a sample mean of 16 9-year-old girls whose weight is more than 66 pounds. That's the information that this is giving us. Okay, let's do another extension of this. Let's take a look at C. Find the probability that one 9-year-old girl will weigh between 59 and 71 pounds. So let's find the probability that one 9-year-old girl will weigh between 59 and 71 pounds. Again, we're going to start off with x's. So we want to find the probability that x is greater than 59 and x is less than 71. Because we're dealing with a single value, find the probability that one, an individual or a single value, we're going to use that first formula for z when we go to convert it. And notice now that we have two values that we have to convert into z's. We have 59 that we have to convert into z's, and then we have 71 we have to convert into z's. So using that first formula, we know that z is equal to x minus mu over sigma. So to figure out for 59, we have z is equal to 59 minus 65 divided by 4.3. I'm going to do this on my calculator. So 59 minus 65 divided by 4.3. And I get negative 1.40 rounded to 2 decimal places. And then finding our z value for 71 gives us 71 minus 65 divided by 4.3. So 71 minus 65 divided by 4.3. We get 1.40. Okay, so for this example, I want to find the probability that this value is in between negative 1.4 standard deviations from the mean and 1.4 standard deviations from the mean. So I'm going to take a look at my z's. Now we're going to convert the z's into p's. We're going to take a look when z is equal to negative 1.40. So here's negative 1.40. And that indicated probability is 0.0808. And then I'm going to subtract that from the probability that were 1.40 standard deviations from the mean, which is 0.9192. Remember that any time that you're looking for this little slice, remember we're looking for the slice, the probability that we're in between negative 1.4 and 1.4, so we're looking for the shaded region here. You subtract the smaller probability from the larger probability. You use the probability associated with the bigger z value and subtract that from the probability associated with the smaller z value. And we have 0.9192. I'm going to subtract from that 0.0808. Sorry, I'm trying to make sure I put this in my calculator correctly. And we get 0.8384. Okay, so the probability that I select a random 9-year-old girl who weighs between 59 and 71 pounds is going to be an 83% chance. Now let's take a look at this on the other end. Let's find the probability that the mean weight of 28 9-year-old girls would be between 59 and 71 pounds. Oh, hold on, let me go home. Right here. So let's take a look at this example. And again, I hope you can see that we are no longer dealing with finding an individual value. Now we are finding probabilities in regards to a sample mean, right? We want to find the probability mean weight of 28 girls. So now we're dealing with an X bar. So when we go to set it up, X's to Z's to P's, we want to find the probability that 59 is less than X bar is less than 71. And again, we're using an X bar because it's a sample mean of 28 9-year-old girls. So we have 28 of them. Can you imagine a house of 28 9-year-old girls? Good Lord. Okay, so again, what we're going to do is we're going to use that second formula for Z, and that second formula for Z, I'll rewrite it over here. It tells us if we have a sample mean and we want to figure out an indicated probability or a Z-score, we use the formula X bar minus mu divided by sigma over the square root of n. So Z equals, and let's do 59 first. 50, sorry, it should be a 71. 59 minus 65 divided by 4.3 over the square root of n. And remember, n is 28. Okay, so 59 minus 65 divided by 4.3 divided by the square root of 28. So again, I'm going to do the numerator first, 59 minus 65. That gives me negative 6. In my denominator, 4.3 divided by the square root of 28. 4.3 divided by the square root of 28. I get 0.812623. 812623. 812626. With a bunch of decimal places, I think 5 is sufficient. 812623. 8126. Sorry, 23. 23. Or you can plug the whole thing into your calculator. Let me not be lazy about this. Let me erase it. 812623. When we do the division, if I take negative 6 and I divide that by a point, 812623, I get 7.38, negative 7.38. Okay, so the first z-value is negative 7.38. Why is this so ridiculously low? Well, think about it. The average 9-year-old weight should hover right around the population mean, which we already know was 65. So the probability that you take 28 of them, sum them together, so you get the weight of 28 girls, add them together, and their mean weight is 59 pounds. That means that all of these girls have to be super skinny and super small. So the probability of that happening is very, very small. That's why we have such a low z-value over here, right? This group are more than 7 standard deviations from the mean going to the left. So this is a really, really tiny group of girls, and the probability of this occurring is teeny, teeny, tiny. Now let's compare that with 71. So I think you might have an idea of what's going to happen here. That we have z is equal to 71 minus 65 divided by 4.3 divided by the square root of 28. So 71 minus 65 is 6. We already know 4.3 divided by the square root of 28 is 0.812623. 6 divided by 0.812623 is, as we were expecting, 7.38. Now, why is this z-value so big? Well, again, we know that the weights of 9-year-old girls should hover somewhere around 65 pounds. If we pull 28 of them aside, and we take the average of their weights, the probability that it's going to be 71 pounds, it's fairly far away from 65, means that we're dealing with a very big group, a heavier group of 9-year-olds. So the probability that their weight is going to be so high that it's going to be 71 pounds is again, it's pretty far removed from the mean. Here we're saying that this group of kids are 7.38 standard deviations away from the mean, that this group of 28 kids. So this is a particularly large group of 9-year-olds, and they're really far away from the mean. And this is a particularly small group of 9-year-olds, and they're also sufficiently far away enough from the mean. So let's find these indicated probabilities. Now, we don't even talk about standard deviations in terms of 7.38 and negative 7.38, but I just want you to get an idea. I hope you can tell that the probability of finding girls, a mean weight of 28 girls that are between 59 and 71 pounds is going to be close to 100%. Because again, they're pretty far away. This group over here that weighed 71 pounds, that had there were 28 of them that weighed 71 pounds, and this group over here that weighed 59 pounds. And again, there were 28 of them that weighed 59 pounds. These guys were super, super small. These guys were super, super big. Most people, most kids, most group of kids, when you take their means, will lie somewhere between these two. These were two extreme values here. So when we associate these with probability, and again, if you look at the z-chart over here, I'm going to move back over here to the z-chart. It doesn't say this. So if we go to that first probability of negative 7.38, but anything that's smaller than negative 3.5 is going to have an indicated probability of 0.0001. Anything that's smaller than that. If you look over here, negative 3.49 is 0.0002. Anything smaller than negative 3.5 is going to have a probability of 0.0001. And again, so this guy over here is 0.0001. The probability of this bigger value occurring being 7.38 standard deviations, and I can tell on this end, if you're 3.49 standard deviations from the mean, you have a probability of 99.98% chance of that occurring. Anything that's bigger than 3.45 has a probability of 0.9999 or 99.99% chance of occurring. When we subtract the two, the probability of this event occurring is equal to 0.9998. So most of the times, 99.98% of the time, if we have a sample of 28 9-year-old girls, their weights are going to be between 59 and 71 pounds. Anything else would be way too big. Maybe they're not 9-year-old girls. Anything else would be way too small. Maybe this is like a really sickly population of 9-year-old girls and they need some medical attention. Most of them will occur between here. Okay, so let's take a look at one more example to make sure that you are understanding of exactly what we're talking about for these types of problems. And let's take a look at this next example. There's a true IQ test that's called the Wechsler IQ test. It has scores that are normally distributed with a mean of 100 and a standard deviation of 15. So let's take a look at this, and we're going to use those formulas that we were looking at before. Find the probability that one person scores less than 105 on the test. Okay, so we're going to start off, and I'm going to work this one a little bit quicker. We're going to start off with x's, and it's an individual, the probability that one person. So find the probability that x is less than 105. And we're going to convert that into z's. And because this is an individual z, we're going to use the formula z is equal to x minus mu over sigma. So 105 minus 100 is 5 over 15. And 5 over 15 is the same thing as saying find the probability that x is less than 0.33. Excuse me, that z. This is the z value. The z is less than 0.33. This is 1/3 is a decimal of 0.333. And so I'm going to go back to my z chart because we use z's and we convert those into p's. So I'm going to look for 0.33, and it's right over here, 0.6293. And remember that anything that's to the left is the true probability, so you can read it right off the chart. So the probability that z is less than 0.33, this is the area that we're shading. That is the information that the z chart gives us. So that's going to be the answer for this one. So let's take a look at this one. Find the probability that 5 people score on average more than 8. So now we're dealing with a sample mean. So we're going to start off with finding the probability that x bar is greater than 86. We're dealing with the sample mean, which means we're dealing with the second formula. Z is equal to x bar minus mu, and the mean is 100, divided by sigma, which we know is 15, over the square root of n, and n is equal to 5. Okay, so 86 minus 100, that gives us negative 14. 15 divided by the square root of 5. That gives us 6.70820. So negative 14 divided by 6.70820, rounded to 2 decimal places, gives us 2.09. Okay, so we start off with x bars, we convert to z's, and now we're going to convert these z's into p's. So again, convert the z's into p's. I'm going to go to my z chart. I'm going to go to 2.09, which is right over here at 0.9817. So here we want to find the probability that 5 people score on average more than 86. So that is equivalent to saying, so remember that this here we're shading to the right, more than 2.09 units shaded to the right. So that means that we're going to subtract the probability that we get from 1 or from 100%. 1 minus 0.9817. And we get 0.0183. Okay, so the probability that 5 people score on average more than 86 is 0.0183. That's for B. Okay, let's take a look at this next one. Find the probability that the mean of 3 people's IQ on the Wechsler's test was between 105 and 123. So I'm going to find the probability that they're between these two numbers. And the fact that we're dealing with the mean of 3 people means, again, we're dealing with x bar. Let me put One more time, put a little bit more space here. So I'm going to ask you at home to pause this and see what you can do in terms of writing this out yourself. Try to find the indicated, the 3 steps. Start off with x's, convert that to z's, and then convert that to p's. So pause here and see if you can do that yourself. I'm going to work it out. So we want to find the probability that our sample mean, so that our x bar is between 105 and 123. And again, because we're dealing with the sample mean, we're going to use that second formula, and we have 2 z's that we're dealing with. So our first z is 105. We're going to convert that 105 minus 100 divided by 15 over the square root of 3. And our second z is 123 minus 100 divided by 15 over the square root of 3. So let's see what values we get for those 2 guys. And we're converting these x's into z's. 105 minus 100. And I'm going to divide that by 15 divided by the square root of 3. And I get 0.58. For the second one, 123 minus 100. And then I'm going to divide that by 15. I'm going to divide that guy by 15 divided by the square root of 3. And I get 2.66. Okay, so when we take these x's and when we take these x bars, when we take these sample means and convert them to z's, this is what we get. I'm just going to double check that first one. 5 divided by 15 divided by the square root of 3. Yeah, it looks good. So again, we're going to convert these p's into z's. P is equal to 0.58. And if you want to sketch it, here's what we want to figure out. Let's draw a picture of it first. So here's our mean. Remember, this is at 0, and here's 1, here's 2, here's 3. Standard deviations from the mean. We're at 0.58 and 2.66. So this is the little slice that we're trying to figure out. We're trying to figure out what this area is right here, according to this guy. Okay, ready? 0.58 is associated with 0.7190. 2.66 is associated with 0.9961. And remember, you take the area of the higher z value and subtract from it the area of the lower z value if you have a slice. 0.9961 minus 0.7190. And that gives us 0.2771. So there's a 27.71% chance of that happening. So this is 0.2771. Okay, so as an extension, let's take a look at these last 2 parts, and then we'll call it a day, and we'll call it a class. One requirement to join a Genius Club is to be in the highest 99th percentile on the test. What IQ score does a person need to be a genius? So, okay, so first of all, we're dealing with a single person. So we're dealing with this formula. X is equal, so Z is equal to mu. Z is equal to X minus mu over sigma. And also notice what it's asking for. It's asking for the IQ score. So we have to figure out X. And I don't know if you remember, we talked about this at the last lesson. So we have a formula for X itself. And X, if we wanted to get X by itself, we would multiply both sides of this equation by sigma. We'll cancel them out. And then we would add mu to both sides of the equation. So that's plus mu. So X is equal to Z times sigma plus mu. So let's fill in the information that we know. Remember that we're looking for X, and X represents the IQ score. So X is equal to, now we don't know Z, we're gonna find that out in a second. We know what sigma is. We know sigma is 15. We know what mu is. We know that the mean of the IQs, let me just go back here and double check. But we know that mu is equal to 100. Now we're concerned with what is our z-value that's associated with that. So if we want to be in the 99th percentile, what I'm going to do is I am going to look for the closest z-value that I can find to the 99th percentile. Let's see what the closest z-value that we can find to the 99th percentile is. And it looks like it is, sorry about that. Let me try to click on it one more time. If we're looking for the 99th percentile, I just had it and then I lost it again. So 0.9900. It's close as we can get. It looks like it's this guy right here, which is 0.9901. We don't have anything closer than that. That's the closest value to get us there. So the z-value that's associated with the 99th percentile is 2.33. So x is equal to 2.33 times 15 plus 100. So that means if you're at the 99th percentile, you are 2.33 standard deviations away from that value in the mean. And when we go and do the math, 2.33 times 15 plus 100 means that we have to have an IQ score of 134.95 in order to get us into this genius club. So the IQ score necessary for us to be a genius here is 134.95. Let's finish this with E. If 4 randomly selected adults take the test, find the probability that their average IQ test score would allow them to state that they are geniuses. So first of all, I hope you can see again, we're dealing with an X bar. And remember, in order for us to be a genius, we have to have an IQ score of 134.95 or higher. So we have to be in the highest 99th percentile. So that means we want to find the probability that X is greater than 134.95. And I'm using this question E as an extension from D. So we're using this value over here. The fact that anytime you want to claim you're a genius according to this IQ test is that you have to be in the highest 99th percentile. So the probability in the X bar is greater than 134.95. And again, we're dealing with the sample mean, and we're dealing with the sample mean because we have 4 people here. Okay, so let's take a look at what this would look like. Sample mean because we want to find the probability that 4 randomly selected adults have an average IQ that tells them that they're a genius, which means that their IQ has to be 134.95 or bigger. So let's plug it into the formula. And again, we're using that second formula. We're going to convert this into z's. Z is equal to 134.95 minus 100, right? Z is equal to X bar minus mu divided by sigma, which is 15, over the square root of n, which is 4, because here we're dealing with 4 people. So I'm going to get on my calculator and do this 134.95 minus 100. And then I'm going to divide that by 15 divided by the square root of 4, which you can just put in 2 if you want. You know, the square root of 4 is 2. You can leave it, it's up to you. And then we have 4.66. So the same thing as saying find the probability that Z is greater than 4.66. Why such a large Z value? Well, the probability that 4 people clustered together have a mean that gives them a genius is very, very rare. 4.66 means you're 4.66 standard deviations from the mean. Remember, most of our data occurs within -3 and 3 standard deviations from the mean. So these are outliers. This is a group of quintuplets that are brilliant geniuses. So let's actually associate this with the probability. Now, again, if we were to shade this, find the probability that Z is greater than 4.66, is this teeny tiny little sliver, right? Here's 4.66 standard deviations from the mean, bigger. And when we go and check this on the chart, anything that's greater than 3, here's 3.49, 3.49 is what it goes up to. Anything that's greater than 3.5 is going to have an indicated probability of 0.9999. But remember that 0.9999 gives us this. It gives us the area to the left. And to find the area to the right, we subtract it from 1. And so this is equal to saying 0.0001. The probability of finding 4 people that have an average IQ that gives them a genius IQ is very, very small. These are people that are off the charts intelligent. So the probability of this occurring is slim to none. It's very, very small. Okay, so that's it for this chapter 6.4 of the central limit theorem. And really make sure that you understand the difference between when you're looking for the probability of a single individual and when you're looking for the probability of a sample mean.